I started off in Cambridge as a mathematician for my first year, but I soon realised that the medics were having much more fun than the mathematicians, so I swapped to do medicine because it seemed a much more fun group to be hanging out with. And I really enjoyed the medical training, and I went to clinical medicine at Oxford, and I loved that. And at that time, a new field was burgeoning called neural networks. So in our lab, what we try to do is reverse engineer how humans control movement. From our point of view, we try to reverse engineer how people control movement by applying ideas from optimal control theory, from statistics, from machine learning, to try and decode how we do that. And our approach is we develop models which could be operating the brain, and then we have virtuality and robotic interfaces where we can precisely control what people see and what they feel during new motor or movement tasks to basically tease apart between different theories. I guess one interesting question to ask is, why is it that some people are more skilled than others at skill tasks? Why is it that someone can knock a small white ball into a hole several hundred yards away using a long metal stick and earn hundreds of millions of pounds in our society? Well, the reason society values that is because it's a hard task to do. We can ask, how well are we doing building machines which can do what humans can do? And if we ask, how well are we doing building machines which can decide what piece to move where? And we put Gary Kasparov, for example, against IBM's Deep Blue, well, the answer is that IBM's Deep Blue occasionally wins. And I expect if IBM Deep Blue played probably anyone in Cambridge, it would win every time. And the reason that problem is so easy is that effectively we know the algorithm or the computer code required to solve that problem. A 5-year-old child could tell you that. Look at all possible moves at the end of the game and choose that move which is going to make you win, guaranteed. So I think it's quite interesting to illustrate really the difference at the moment between building machines to do human tasks and where human performance is. And in fact, I have collaborators in Germany at the DLR Institute who lent me this video, which basically shows the end of a PhD of a student training this robot to pour a bottle of water into a glass. Now, this is a hard problem because as you pour a bottle, the water sloshes about, so it's actually quite a tricky robotics problem. But at the end of the 3 years, as you can see, the robot can do it, but effectively it does it in a very poor and slow way. And if you now wanted this robot to do some other task, well, that's another 3-year PhD program, because there's no generalization really from learning one task to another. But if you compare that to maybe the pinnacle of human performance, and I'd rather like this example of cup stacking. It's a very popular sport in America, college students and high school students. There are 12 cups you have to stack and unstack in a particular order against the clock. And in fact, this is the previous world record, Emily Fox, performing it. And she is able to unstack them and stack them in an amazing speed and precision. And this is actually a video of her winning the world record. And we come nowhere close to understanding how this can be done. So I hope if we can extract what the learning mechanisms are the brain use, we can apply them in 2 different things. First of all, we could apply them to rehabilitation. We could facilitate rehabilitation after disease, where, for example, after stroke, relearning is a really important part of therapy. And secondly, we could apply them to machines, and hopefully build machines which could learn in the same ways that humans do, and that would really be a fantastic advance.